In this video, I'm going to talk about the t-test, which is a method to compare the means of two groups defined by a single categorical variable. We are going to start, as always, by an exploratory data analysis that motivates the following work, and then do the frequentist model fitting and the Bayesian model fitting. As in previous videos, all these codes and data to run this analysis are in the website shown in the screen. So the general linear model analyzes the effect of a numerical or a categorical explanatory variable or variables, if there are many, on a single numerical response variable that has a normal distribution. The t-test is one of these instances that allows comparing the mean of the response variables among the levels of a categorical explanatory variable, and therefore this is a special case of the general linear model. So, as in previous videos, the response variable then has a normal distribution with a mean and a variance. In this case now the mean is defined by the index k, which varies between 1 and 2 because there are two groups. In R, this model is written as follows. The response variable again follows a normal distribution, but now we write the mean in the following way. We now define one of the two groups as the reference group, and we call it ref, and alpha, which is the differential, the difference of means, which can be positive or negative between the reference group and the other group, and sigma square is the variation, or is the variance that reflects the variation of the response variables around its mean. Instead of estimating the means of the two groups, sigma y1 and sigma y2 are, and most other statistical software equivalently estimates the mean of the reference group, the difference or differential of means between the reference group and the other group, and of course the variance of the response variable. The only difference between this case, where we have a single explanatory categorical variable, and the simple linear regression where we had a single numerical response variable, is shown in the following diagram. In this case, the categorical explanatory variables, we change from the reference group to the other group, and therefore we obtain the differential between the means represented by the dots, and here the slope simply represents the change of the mean of the response variable when we change one value from x to x plus 1 of the numerical explanatory variable. In both cases, the model is the same. It's just that in the model represented in the left, the explanatory variable can only change between two possible values or levels in this case. We start again as usual by importing the data. The data concerns a natural experiment done in Arizona in the US, and the goal is to evaluate whether the length of the horn of a lizard differ between the lizards that were killed by a bird predator and those that were still alive. So we then have the response variable horn length and the categorical explanatory variable survival with two levels, killed and living. Here we have the usual descriptive statistics for the response variable. We make a box plot to show that the medians represented by the line of the two groups differ between the groups, and the means represented by the decreased square differ between the groups as well. The variation between the groups looks as evaluated by the width of the box looks similar between the two groups. So in response to this question, yes, the variables seem to be related, since the mean or the median of the response variables differ between the levels of the explanatory categorical variable. We can also compute decreasing statistics by group by first defining a function that, given a vector x, here's the start of the function, here's the end of the function, calculates the mean, the median, the standard deviation, and the number of data points. So this is yet another representation of the same information shown in the box plot. We also see that the mean differs between the two groups by 2 units, or 2 centimeters, and that we have quite a different number of data points per groups. So as in previous videos, we use the package fit plus to obtain the QQ and CDF plots that allow to ascertain whether which probability distribution is best to model the response variable. And here we see the two candidate variables that we are contemplating in this case, which is the normal and then the log normal distribution. I think it's very clear that the normal distribution is quite better than the log normal one, but there is a clear difference in the lower tail of the data, in which neither of the two distributions fit the data well, but the normal seems a lot better than the other one. So we start by doing the frequentist model fitting. The model M1 is a linear model. The response variable separated under categorical variable, and the summary is the following. We have the descriptive statistics of the residuals, which are of no use. The coefficients now indicated the intercept and survival living. Let's recall that the statistical model for this data is that we have the mean of the reference group, and alpha is the differential of means between the reference group and the other group. So here we have the mean of the reference group. The reference group is arbitrarily given by R using the alphabetical criterion, which is of course nonsensical, and you can change that. So this is the mean of the group that does not appear. The reference group is therefore killing, and survival living says that this is the alpha, the differential of means between the reference group and the other group living, which is of 2 units, 2.29. So we have the standard error of the mean of the reference group, and this p-value simply says that this mean of the reference group is significantly different from 0, which is of no interest to us. More interesting is that this is the difference of means. This is the standard error of the difference of means, and this p-value says that this difference of means is statistically significant. So here we see again that killed is the reference group up to rounding errors, and the other group living has a mean of 24.3, which is roughly this difference of means between the two groups. We also, by raising to the square the residual standard error, we obtain an estimate of the variance of the response variable. So what R does to solve this model, this linear model, is that it creates a model matrix with a binary response variable, assigning 0 to the values of the reference group and 1 to the values of the other group, in this case living, and fits this model matrix to fit this model as if it were a linear regression. The package Broom allows to gather the input necessary for the residual analysis. This is what's done before, and therefore I will not explain it yet again in this video. This is just showing the first of the 194 lines of this data frame res.m1, and with this input we obtain the codes for the residual analysis. What we see here in the first plot of the standardized residuals against the fitted values, we see two groups, which is of course what we have. So let's focus then on each of these two clouds of points. The cloud in the left corresponding to the mean corresponding to the values of the reference group. We see quite a similar scatter in the negative and positive sides of 0, and here we see a slightly bigger spread in the negative side of the residuals than in the positive side of the residuals. This shows that the fit is not exactly the best that we could hope. The plot of the residuals against the explanatory variables show that the median of the residuals are both similar, close to each other and similar to 0, which is a good sign. That the variation, as indicated by the width of the boxes, is quite similar between the groups, which is very good. But we see again, as we saw before, that the scatter of the residuals of for one of the groups in the negative part is quite larger than the scatter in the positive side. The QQ plot shows that the data is close to the normal distribution, the response variable is close to the residuals, and therefore the response variables is close to the normal, to the perfect fit shown by the line of a normal distribution, except for the lower part of the lower tail of the data. And here we see in the Cook distances that there are a few points, about two, which seem to have an inordinate potential influence on the fitted values of these parameters. So the model has a somewhat poor fit of the data. So what I did here is to identify the points that have either a big distance, a big Cook distance. By Cook, I arbitrarily chose bigger than 0.4, and these are the lines of the data frame that have Cook distances bigger than 0.04, and here is the lines of the data frame which has a standardized residual lower than -2, meaning all this, and these are these are the lines of the data frame. So what we are going to do is to refit the model without some of this data to assess whether the model refitted with fewer data points has very different parameter estimates compared to the model fit with all the data points. So here is I deleted 3 data points that combine having a high Cook distance and very low residuals. And here is the model fitted with all the data. So what we see here is that, well, there are some differences in the values of the difference of means, not in the sign, not in the significance. There are some minor difference in the variance, or the standard deviation rather, of the response variable. The R-square marginally increased when we or differ between the two fitted. So there were changes in the magnitudes of the mean of the horn length for the kill group that showed a difference of 2.1%, and the difference of the magnitude of the difference between the means, the alpha, the differential of the means, which had a difference of minus 17.8%. So the residual standard error also changed, and that change expressed as a percentage is plus 9.1%. So the question is now what to do. I believe, and this is not based on theory but rather on an ethical standpoint, that we should explain that some of the qualitative differences between the two models by showing the two outputs to whoever requested the analysis. So in order to communicate the results, we obtain a table, which is a kind of a data frame with the parameter estimates and the confidence intervals of the parameter estimates, interpreted in the usual way. The conditional curve obtained with the package ggfx shows the predicted means and the standard and the 95% confidence intervals for each of the two groups, with which we make the following plot, and this is what we can easily communicate as a result of this analysis. As for the Bayesian model fitting, we proceed as follows. We recall the statistical model that is independent of the procedure that we use to estimate its parameters. So it's key to be able to write this model in order to define the priors of its parameters. So we use the getPrior command of the library VRMS that shows the intercept, which corresponds to the mean of the reference group, the mean of the response variable for the reference group, B, survival living, which is the differential of the means between the mean of the reference group and the other group living, defined for the categorical explanatory variable survival, and sigma, which is the standard deviation, not the variance, of the response variable. So this by default, this package BRMS defines weakly informative priors. So I decided to define alternative priors for each of the parameters. I'm going to discuss them after I plot them below. So the priors that I defined show that I expected the mean of the response of the reference group of the response variable to be centered at the most likely value to be 20, and I expect as many low values smaller than the mean and as many values higher than the mean, and that 95% of these potential values of the mean of the reference group, the mean of the kilt mean Horn length of the kilt group to be between 10 and 20. This shows that I expect pretty small values of the differentials of the mean, and that I expect as many values of the negative differentials and as many positive differentials, and that I expect low values of the variance of the standard deviation of the response variable to be more likely than high values. The model again is shown, the fitting of the model is shown here. Here is the formula of the model. Here we identify the probability distribution that we use for the likelihood part of the model, the priors shown in the previous slide, the data, where the data is in this data frame, and the rest is essentially explained that we are asking for 3 chains of this Hamiltonian Monte Carlo algorithm of 2000 parameter estimates each after discarding the first 1000 values obtained. The summary of the model is shown here, and it can be divided in 2 parts. First, the marginal posterior distribution of each of the 3 parameters. Estimate means the mean of this marginal posterior distribution, and here we have the standard deviation, which here corresponds standard error of this marginal posterior distributions, and the 95% credible interval. The 95% credible interval for the differential of means ranges between 1.28 and 3.27, meaning that values smaller than 1 or smaller than 0, that is negative, are highly unlikely. The remaining part of the summary contains metrics of the convergence of the chains, the R hat, and the effective sample sizes of each of the 3 parameters. We are going to assess the chains. Although the chains appear to have converged to a common posterior distribution, we are going to assess this convergence with the usual plots. And the usual plots are the posterior distributions for the marginal posterior distributions for all parameters of the 3 chains. Notice the wobbly nature of these distributions obtained by the Hamiltonian Monte Carlo algorithm. We show the autocorrelation of the sample estimates, showing here in this plot that the autocorrelation is pretty small, that is smaller than 0.1, that is essentially statistically independent values, separated by 5, 10, 15, or 20 iterations of the chains for all parameters of this model. In the degree of mixing of the chains shows that for each of the chains, the 3 chains have more or less sampled or explored the equivalent ranges of the parameters, equivalent set of values of each of the 3 parameters. That is, no change got stocked in very high or very low parameter values for many of these iterations, showing that a very good degree of mixing of the chains. So in order to assess the goodness of fit of the model, we obtain the probability distributions of the Pearson residuals and of the fitted values and summarize them. That is, we obtain the average and the standard deviation, and if we wish, the 95% credible intervals of the residuals of each point. This was explained in the previous video of the simple and multiple linear regressions. Here is for the residuals, and here is for the fitted or predicted values. With these values and with the explanatory variables, we made the following plots. So first we see the plots of the residuals, again the fitted, values, and we see essentially two clouds, and this is simply because all the value we essentially have groups whose means are segregated, one range around 22 millimeters and the other around 24 and a half. And so we see that the ranges for the left cloud, we see that the ranges of the residuals in the positive side that is pretty similar to the ranges of the residuals in the negative side. This is at least good for one of the two groups. For the other group, we see that the variation, the range of the variation in the positive part is smaller than the range of the variation in the negative parts of the residuals, suggesting a not so good fitting. Regarding the plotting of the residuals against the explanatory variables, we see now in a box plot showing that the median of the residuals are both similar and close to zero, and the variation of the residual is, as assessed by the width of the box, is pretty good and pretty similar between the two groups, although one of the two groups, the group corresponding to the living, has a larger range of variation in the negative part of the residuals, which is exactly what we saw in the first graph. The QQ plot shows that for most but not all the set of values of the response variables, we have a pretty good fit to the normal distribution as we would expect for a good model, but not for the lower tail. So the model has a mediocre fit to the data. Possible improvements include considering another distribution, probability distribution, to model the response variables and adding other explanatory variables. As for communicating the results, we obtain the conditional effects plot, which is the mean of the posterior distribution and the 95% credible interval for each of the two groups. And we can also show the 95%, the means and the means and 50% credible intervals. This is the blue dark line, and the 95% credible interval for each of the three parameters. So this concludes this video, in which I talked about the t-test, a method to compare the two means of a response variable that has a normal distribution, in which we had the exploratory data analysis, the frequencies model fitting, and the Bayesian model fitting. Thank you very much.